So let's take this problem again, hyperdiffusion, and say, let's solve it a completely different way. No Taylor expansions. In fact, you know what I'm going to do? I'm going to Fourier transform everything spatially. Okay? I'm going to ask, is the stiffness due to the scheme, or is it really inherent in the equation? So if I take a Fourier transform in x, I'm going to get on this side. Fourier transform of this times derivative is equal to minus c. If you remember, the Fourier transform of the fourth derivative is I k to the fourth power times the Fourier transform of the function itself. I to the fourth power is 1. Even an Oregon duck might know that fact. I'm just saying. Probably not the football team, but. So I did have this guy once in my class. This is a couple of years ago. Like, remember our 0 and 12? I hate to mention in class in public, but we did have a bad season once, a couple of years back. And I was always a little bit making fun in class. This is an undergraduate class I was teaching, and it was kind of big in an auditorium, 100 people. And I was just, every Monday, I just couldn't help it. Guys, did you see the Husky? I mean, this is, you know. And then halfway through the quarter, I'm putting my stuff together at the front, and this dude walks over. I'm like, man, that's a big dude. And he's just like, you know, he's about as wide as he is tall, and he's, hey, can you sign my form? I got some games to go to. He was the linebacker for the Huskies, and I was like, please don't hurt me. I didn't make any more fun. He was super nice, but I felt I kind of had it coming. He should have punched me, probably. I deserved it. Anyway, I didn't get beat up in class. I had the opportunity. It's sometimes good to be a smooth talker. You just kind of work your way out of that one. Oh, yeah, no, awesome. Yeah, dude, that's all. Wait, linebacker, that's all. You playing? I did just enough to get out of trouble. All right. Anybody here? See, now I can talk them up big because they're winning now, so it doesn't matter. Here is our equation in the Fourier domain. I have a k to the fourth, and I'm taking Fourier modes. You remember, these k's go like n's, so I get to pick my n's. Remember, these are like cosine 1x, cosine 2x, cosine 3x. And so let me give you some numbers here. Suppose I solve this problem, and just like before, you get to pick the number of Fourier modes. Right? You say, I'm going to discretize. So I'm going to chop this up into, and that's going to determine your Fourier modes. So suppose I pick, for instance, I will solve this problem with 128 modes, which isn't very much. The k's then kind of range from like negative 64 to 64. These are my, from cosine negative 64x to cosine 64x. Okay? That's what I got. And, okay, that's fine. Now, I'm going to plug this in here, and this is for all the Fourier modes. What's 64 to the fourth power? So it turns out 64 to the fourth power is something like 10 to the sixth. That's a pretty big number, isn't it? Isn't OD45 taking step sizes around with errors of 10 to minus 6? So you imagine when you step forward in the future, some of those coefficients out there that should be 0, you're going to multiply them by a huge number. So all of a sudden it forces the code to say, wait a minute, these things that are supposed to be, I got to take much smaller steps. Otherwise, this here is a huge number. So even if it's way out there at these high frequencies, it's supposed to be very small. I'm multiplying something very small by something huge. It gets worse. I mean, you can imagine 64 is not that many modes. I could take something like more reasonable, which is 1,000 Fourier modes, okay, or 2,000 if you want good resolution. I'm just pick 1,000 here. So then it's 10 to the 3 here, right? And then you're going to raise that to the fourth power, and that's going to be 10 to the 12. So you take something small and raise it to the 12th power, or have a coefficient amplifying it by 10 to the 12. What that forces your code to do is take really small time steps. This is the manifestation of numerical stiffness in a Fourier mode sense. Okay? And the k to the 4th comes because you have 4 derivatives. So this k to the 4 is playing the same role as your divide by delta x to the 4. Okay? That's a problem. You don't ever get around the numerical stiffness issue. It's a problem for you if you have high derivatives. You're going to have a slow code. Okay? Just breaking it to you. All right. So hopefully, the most important issue in your life in the last half hour, you're getting the idea of how much it is important to you if you're going to write a code with high derivatives, because it's going to basically just slow you down. That's the main thing. So let's talk about ways to get around this. Okay? So ultimately what we want to say is, okay, there's a problem. Hey, don't bring your problems to me. Bring me solutions. See, that's what the suit guy says. I want solutions, not problems. I can't do math, but maybe I can do that. All right, ready? So solution time. This is where I shine. Ready? Solution time. Get somebody else to solve your code. That's the first thing. Now, if you can't get that, here's some tips. All right. Number 1, use variable time stepper. Or what they call adaptive stepper. Adaptive stepping. So the idea is, this is all about picking your delta t. Delta t is the biggest problem, right? So what you want to do is you say, how do you pick your delta t to begin with? Right? So in your problem, your solution is changing in space and time. When your solution is changing slowly, you might be able to take big steps. If your solution is changing quickly, you better take small steps. Right? And you should build that into your code. Here's what's awesome. All the ODE suites of solvers in MATLAB, ODE 1.5, 1.5s, 1.3, 4.5, 2.3, all of them have adaptive stepping. They try to take as big a step as absolutely possible while preserving an accuracy of 10 to the minus 6. Fantastic. In other words, if you write your own code and you just have a fixed delta t, how do you know you can't take steps that are like 10 times bigger in certain parts? Because sometimes when you have stuff, so for instance, think about the following problem. I have 2 waves running towards each other. I can take pretty big steps, and right when they collide, a lot of stuff happens. If you actually watch what would happen if you were to do adaptive schemes, big steps, small, big steps. Now, if you were to write your own code and you have adaptive stepper, if you want to get this right, you have to take small. Okay, come on. Just so you get this little part right. That's stupid. Adaptive stepping is what you want to do. And it's built in. And by the way, so the fact that it's part of the code tells you how important it is, right? It doesn't give you a choice about adaptive stepping. It's just going to do adaptive stepping, period. That's how you do scientific computing. So this helps a lot because partly it can try to address this issue of numerical stiffness. If it gets forced to take small steps, it will. But when it goes like, hey, you know what? I can kind of get big steps out because, right now at k to the 4th, this thing's really small, like 10 to the minus 14, so I can maybe get away with big steps. Okay? So that is number 1 thing. That's also why I kind of advocate, one of the beauties of MATLAB, right? One of the beauties of MATLAB is if I asked you to write an OD 4.5 code, 4th order Rangakata, if you look at the routine, it's not so bad. That's easy. Now I'm going to ask you, okay, let's ramp it up. I want you to write a code to pick delta t that gives you 10 to the minus 6 accuracy, and then I want you to do adaptive stepping. Right? All of a sudden, your little OD 4.5 code is just getting huge, right? And it's not clear you could write it as efficiently as the people they hired to do this professionally, right? So there are people who mock MATLAB. They're all around, especially the hardcore coders. Oh, MATLAB's that's for children. It's like, yeah, I'm a child because I'm not going to write that, right? I'm not. I'm going to just use this power that's there. Now, if I were going to do supercomputing and I was going to have some huge thing, then yeah, okay, then you have to write your own adaptive step or write your own stuff. But you know what? I got more important things to do. I got a cappuccino to make after this class. Do I need to be writing code like that? No. I got some work, some latte art. All right. I have my priorities straight. Hopefully you do too. If numerical stiffness is a problem, and by the way, how do you know it's a problem? Typically, the dead giveaway of numerical stiffness, high derivatives. That's your starting point. You got a lot of derivatives to take on something spatially, you got numerical stiffness. And in that case, you want to use things like OD113. Why do you want to use OD113? Because OD113 is trying to take advantage of the implicit schemes. It's a predictor corrector. It's saying, I have a problem with time stepping and the CFL condition. What I know is the implicit scheme probably has awesome CFL properties. Lets me take really big steps. And this says, how about we try to make use of that? I'll still make it an explicit scheme, but the predictor corrector predicts the future and then uses that in the implicit scheme. Okay? So that's there. Variable order predictor corrector. Okay? Through. Here's another one. If stiffness can also come in a different way, which is from the physics itself. What I mean by that, or biophysics, whatever you want to call it, engineering, physics, whatever. If it's part of the problem itself. So for instance, you have certain problems where there's rapid transitions in behavior. So for instance, there's some of these chemical oscillator problems where these two mixed states will transition from one to the other. And you can even YouTube some of this. There's these cool experiments where these two chemicals are interacting and it turns into one, switches over. It happens very rapidly. Now, if you are solving this thing on a computer, during the regions where it's kind of just doing this kind of one state, you take huge steps, and all of a sudden you hit this wall. It's not being generated by high derivatives. It's being generated by the fact that there's rapid transitions in the solution. And if you do not catch that, you're in trouble. So if there's stiffness from the problem itself, where you have rapid transition regions, then there's this thing called OD15S. These are called gear methods. And basically what they are techniques, just like predictor corrector. They're fancy techniques for saying, hey, I gotta handle these issues. Do I have a better time stepper than just saying, oh, all I'm going to do is just take delta t to be smaller, 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 smaller? Is there a way I can sort of say, maybe I have a better prediction way when I can get a better prediction about what the solution is doing? I won't talk about them, but OD15S, the S stands for stiff. Okay? Final comment. The general method you should just kind of, that most people apply. Something like OD23, OD45. So we could talk about all this, and so this is already integrated. Stuff like this, in some sense, how do you know to use this? You don't often, except if you have high derivatives, you might already know that you got this to use. Sometimes it depends. Maybe a fourth derivative, it's still a wash whether you use OD45 or 113. You have to kind of play around with it. Generically, I always just say, look, I advocate just try OD23 and 45. Those are sort of pretty great schemes, pretty great stability properties when it comes to CFL. They're kind of the dominant paradigms for how you step forward in time. However, when you have a problem with high derivatives, it's always good to say, you know what, and this is so easy to do in your code. You take this code that says this, you put your cursor there, and you backspace twice, and then you put those numbers in, and your code's changed. Okay? And sometimes it's really good to do that and compare your results. Let me run this out, and let me run that out. Now, if you see a difference, boy, warning bells should go off in your head. Like, ooh, something's going on here. There's something wrong here. Okay? And you can easily backspace again, put 15S in there. So these are your generic techniques. And part of the reason you know to use these comes from lack of anything else, experience. How do you know this is going to change? Well, you know, if you know something about the problem, something about the behavior of the system ahead of time, you make use of it. But it's not like you look at the equation, oh, I see that this equation is going to change rapidly. You never know that stuff until it's too late. Okay?